In this video, we're going to be discussing how to apply Fourier series to functions that may be defined in intervals like this. So we may have something like 0 to L, and then the function looks like this. So it is possible, because essentially with a Fourier series, we want to define it within symmetric intervals. So we want them to be symmetric about the y-axis. So we're going to have our function here. And there are two choices that we can have. So the first choice is we can expand this function as an even function, which means that this is just going to be a mirror projection between that. And then in the end, what we're going to get is we're going to get a periodic function that is going to repeat like this over and over, and that the period is going to be 2L. Now alternatively, but what we can have is we can expand this as an odd function, and that means that instead of having it here, we're going to have it flipped over. So that's just going to be, I guess, antisymmetric, if you can call it that. So the function is going to look like this instead. And then when we actually go, because it's going to be periodic, it's going to keep repeating like this over and over again on both sides. So it's going to go through here, and so on and so on. So depending on our choice of what we want to do, in terms of the expansion, we're going to choose one of two possibilities. So for the even case, our Fourier series is going to be a Fourier. It's going to be a Fourier sine series. So what I mean by that is that if we choose an even series, we're going to have a Fourier, actually a cosine series. Sorry. So it's going to have a naught plus our old friend an cosine n pi x over L. So because basically we know that for an even function, our sine term or bn coefficient is just going to be 0. So this is what we're going to have. And then that means that we're going to define, so I'm just going to do this down here. So if we perform an even half range expansion, then we're going to get this infinity of an cosine of n pi x over L, and then we're going to have our Fourier coefficients defined within that half range, because remember the function is only defined within that half range. What we're doing is we're creating a virtual version of that function, and because that we're creating a virtual version, we cannot just count that in. What we're doing, this is going to aid us to actually find the Fourier series expansion of this little function here. So we're going to have the following. This is going to be half of the original period. So normally you would divide this by 2L, but now the range is from 0 to L, so you just divide this by L, and then this is going to be the integral. So now it's going to go from 0 to L, so that's the interval in which the function is defined. So that's the interval you're going to take for your Fourier coefficients of f of x dx, and then an is going to be the following. It's going to be 2 over L, because remember that with a full range from minus L to L, we had 1 over L. So now you have half that range. So if you half L, then you get 2 over L. So this is going to go from 0 to L. And this is going to be f of x sine n pi x over, actually it should be cosine n pi x over L dx. So those are our two coefficients, and then bn is just going to be 0 all throughout, because we're taking an even function. And basically for an odd function, we're going to have the following. We're going to have a Fourier sine series, because a naught and an are both going to be 0 for an odd function, as we discussed previously, because the two areas are going to cancel out. So we're going to have this defined simply as the sum of the sine series, n equals to 1 of bn sine n pi x over L, and then we're going to have the Fourier coefficient bn is going to be equal to 2 over L from 0 to L of f of x times sine n pi x over L. So now that we have made this definition, we can actually apply it to a problem. So let's have, I'm just going to get rid of this so we can work with it. Let's go back to the top. And let's consider a simple function. So let's have a piecewise function that is defined on the range 0L. And then at L/2, we have this. So we have a triangle function. So this is f of x, x. And let's define the height as k. So basically the way we're going to write this mathematically is as 2k over Lx from 0 to x, x between 0 and L/2, and then 2k over L minus x for the range L/2 x L. So what we're going to do first, obviously we need to calculate we know that we need to decide, are we going to expand this as an even function? So if we do an even expansion of this half range, it's going to look like this. And if we do an odd expansion, we're going to have the following. So it is going to look like a triangular form of a sine wave. So we need to choose which one we want to do, because that's going to take on a different Fourier series expansion. If we do the even one, we're going to have the Fourier cosine series. And if we do the odd expansion, we're going to have the Fourier sine series. So in this particular example, I want to use the cosine series expansion. So we're going to choose an even expansion in this case. So that means that our f of x is going to be represented by a0 plus sum n equals to 1 of an cosine n pi x over L. So now what we're going to do is we're going to find these two coefficients. So the first Fourier coefficient is going to be a0. So we know that this is defined as 1 over L from 0 to L of f of x dx. It is just the average value. So basically what we're doing here is we're taking the area underneath that function within this interval, and then we're dividing it by the size of the interval, and that's going to give us the average value. But here we have a triangular function, so we can do this very easily by simply using geometry. So we know what the area of a triangle is, so that's what we're going to do here. So we know the area of this triangle. So this is actually going to be 2 times that, because it's going to be a rectangle. This area is symmetric to this one, so we're going to have the following. The area is going to be equal to base times height, so that base is L and the height is k, and then we're going to have, and now because we want the average value, that means that a0 is just going to be 1 over L times the area, because this integral is just the area, so this is going to be equal to k. So that's the value of a0. We didn't have to integrate to find that. So the next thing we want to do is we're going to find an. So this is going to be equal to 2 over L of the integral from 0 to L of f of x times cosine n pi x over L dx. So this is going to be 2 over L. And now we're going to have a massive integral, because we're going to have to split this into 2 integrals. So we're going to have from 0 to L over 2, we're going to have x cosine n pi x over L dx plus 2k over L from L over 2 to L of the function L minus x times cosine n pi x over L dx. And now what I can do is I can factorize this 2k over L out. But before we do that, obviously we need to evaluate each of these ones. So let's call this one integral 1. And let's call this one integral 2. Because we're going to have to use integration by parts for each of them. So let's evaluate integral 1 first. So this is going to be equal to Lx over n pi sine n pi x over L minus L over n pi 0 to L over 2 sine of n pi x over L dx, and this is going to be evaluated from 0 to L on 2. So that means that this is going to become L over n pi x sine n pi x over L plus L squared over n squared pi squared cosine of n pi x over L evaluated between 0 and L on 2, and this is going to become equal to L squared 2 n pi sine of n pi over 2 plus L squared over n squared pi squared cosine of n pi over 2 minus L squared, I believe. So let's just check for the sake of argument. So we're gonna have for the first one, we're gonna have L on 2, so that L cancels out with this one, and we know that for any multiple integers of pi we're gonna have 0, but in this case we would have, instead of multiple integers of pi, we're gonna have the following expression: n pi over 2. So obviously this is going to have values of pi and 2, 3 pi and 2, which are actually values 1, minus 1, and so on. So we cannot just ignore that. So that's why we included it in this case. And similarly for cosine, we're going to have n pi on 2. And then for the case when we have 0, we have 0 here. So that means that this term vanishes. And then we're going to have 0 here, that becomes 1. So this is going to be L squared over n squared pi squared. Alright, so that's going to be integral 1. Now to evaluate integral 2, we're going to apply the same sort of procedure. We need to use integration by parts. So for integral 2, we're going to get L squared over n pi sine n pi x over L. So that's this integral here, because basically we're gonna separate this by using the sum of integrals, and then we're going to combine the results. Lx over n pi sine of n pi x over L plus the integral of L over n pi sine of n pi over x over L, and then all of this evaluated between the limits L on 2 and L. So you can see that this is a fairly complicated procedure, even for this very simple triangle function. We have gone through this whole process here, and it's a lot of integration. Integration by parts is probably the one thing you will be using the most with this kind of thing. So this is going to be equal to L squared over, it's just going to be L. Going to factorize the L over n pi, and that's going to leave us with L minus x sine of n pi x over L minus L over n pi cosine n pi x over L, and this is going to be from L on 2 to L, and hopefully in the end, so after you evaluate this, you will reach an expression like this. So it will be L squared over n squared pi squared minus 1 to the power of n plus 1 minus L squared over 2n pi sine of n pi over 2 plus L squared over n squared pi squared cosine of n pi over 2. So really this is just an exercise of substituting and then applying, evaluating those functions here and seeing if you can find any kind of simplifications here. But essentially sometimes you might get really big expressions like this, so really there's not much you can do about it. You have to write your Fourier series expansion in terms of that. So in the end, we're going to have the term an is going to be equal to 4k over L squared, and that's going to be 2L squared over n squared pi squared cosine n pi on 2 and minus L squared n squared pi squared plus L squared n pi squared minus 1 to the power of n plus 1, which is the same as 4k over n squared pi squared 2 cosine and that's our final answer. So now we have the two Fourier coefficients. All we need to do is set them up into the Fourier series expansion. So we know that our final expansion is going to look like this: k plus an, I'm just going to write it like this because it's a fairly long expression, n equals to 1 cosine of n pi x over L. So that's your Fourier series expansion for this half-range function when we expand it as an even function. And you can imagine that if you choose an odd function, you're going to have to find the Bn coefficient, which will correspond to the Fourier sine series, whereas this 2 would be 0 for that particular case. So hopefully by now you're pretty clear on how Fourier series expansion works, how to define an interval, how to perform half-range expansions in the case you're given a function like this that doesn't actually have go all the way to minus L, when you have a generic period L as well, and how to apply simplifications based on whether the function is even or odd within that interval. And from now on, what we can do is we can finally apply this to solving boundary value problems involving partial differential equations.